So I'm trying to give a quick or brief overview in this talk about different topics that I've been working on. And so just to focus on a common theme, I've tried to pick engines that produce mechanical work, either as a heat engine or as an active engine. And so the general idea or the general type of system that we are working on are small non-equilibrium systems. That means we have some system in a black box in contact with the heat bath, and it's driven from outside, for example, by chemical forces, or it could be driven by mechanical forces. And on the other hand, these systems, they produce some output. So for example, they produce some chemical molecules. If it's a motor, it might produce some displacement. And what is common to all of those systems is that they produce some heat that is dissipated into that heat bath. So the fundamental question that we are asking is, how can we understand how these driving forces affect the outputs? And because it's a small system, these outputs will be fluctuating. And so we are asking if we can measure these fluctuating outputs. What do those fluctuations tell us about the system itself? And so as a kind of mathematical framework, we are using Markovian networks. So we are discretizing the state space of the system into states I and j, for instance. And we assume that there are transition rates kij leading from one such state to another one. And then we impose the principle of local detail balance. That's really the connection between the mathematics of that network and the physics. And you might know that detailed balance expression for equilibrium systems, where you just have the energy change from I to j in there. But to model a non-equilibrium system, we also add the driving, that is the turnover of free energy that comes with such a driven transition. So for example, if we have a chemical reaction driving a transition, then we are adding the chemical potential difference here, or we might add the mechanical work if it's driven by some mechanical force. And then we can, in the steady state, calculate the rate of entropy production. It's a kind of quantifier of how far we are from equilibrium by just looking at how much energy is turned over on average in that whole system. Then we can look at a fluctuating current, for example, how many molecules are produced or how much is that weight lifted in some given time. And we can look at how that current fluctuates over time. And using that network language, you can build basically any non-equilibrium system. For example, you can try to build a clock from it. Now you could start building a very, very big clock, and you will have big gears in there, and necessarily that will generate lots of heat, and you will need to invest lots of energy in driving that clock. But you could ask, how can you make a clock in general more efficient? And a very simple answer is just make it smaller. So you will have smaller gears and hopefully less friction. And in fact, you can expect that a small watch consumes much less energy as the clock that is driving Big Ben. But now if you try to take that principle even further and you go to smaller and smaller clocks, you can look at a molecular scale. For instance, at the clocks that are operating in bacteria that they use to anticipate the sunrise. And these clocks, they might still work quite well, but the problem is that they are affected by thermal noise. So you can already see if you're trying to make a clock more energy efficient, there is noise acting on it, and that makes it less precise. And that trade-off already shows that there is a kind of general principle, a general energetic cost of precision. And indeed, that has been formulated in the so-called thermodynamic uncertainty relation. And it holds basically for anything that could work as a clock or anything that produces a fluctuating current that should be precise. For instance, you could also look at a molecular motor that is running along a filament that is consuming ATP. So it also has some thermodynamic cost that is dissipated as heat. And you can quantify the precision of that stepping motor by just looking at the variance in the position after some time. And to make that dimensionless, you divide by the mean displacement squared. And now it turns out that if you multiply that cost with the precision, then this is something that is always greater than 2 in natural units. And so that is, again, telling you that the more precisely such an autonomous system operates, the more energy you have to pay for it. And that statement holds for anything that you can model as such a Markovi network, for any time antisymmetric current in it. Just to give you some numbers, if you want to have a clock that is, for instance, 1% precise, then this is telling you that you need to pay at least 20,000 kBT, which might not be much for a large clock, but it definitely is a lot for small bacteria. And it's also interesting to note that this can be saturated for weak driving, so in linear response, but in general, this holds arbitrarily far away from equilibrium. And I promised already that I wanted to talk about heat engines. And so here I'm showing you one application or implication of that uncertainty relation for steady state heat engines. So a heat engine, as you might remember from your undergraduate course in statistical physics, is just some machine operating between two heat baths. So it's connected to a hot heat bath and a cold heat bath. And there is a current coming from the hot heat bath and a current of heat dumped into the cold heat bath. And if it's working well, then it will produce some positive output power. Now you can quantify the efficiency of such a machine just as the output power divided by the heat taken from the hot heat bath. And the famous Carnot result tells us that this efficiency is always smaller than the Carnot efficiency given by the temperatures of those two heat baths. And now a long-standing question has been, can one actually reach Carnot efficiency at finite power? And there were some papers saying, yes, it's possible. Some were saying, no, it's not possible. And so what I think the important insight from that uncertainty relation is that there is actually a third player coming into that trade-off. And we call that the constancy. So you can look at how much power is being dissipated or how much power is being produced in some time interval. And you can also look at how much fluctuations are there. What is the level of fluctuations in that power? Because you would also want to have a very stable machine that produces a very constant power. And now the uncertainty relation links that constancy to the entropy production. So the entropy production here is just given by the entropy produced in these two heat baths. So it's related to the heat currents divided by the temperatures. And now if we know the constancy, for instance, we get one more constraint on these currents, namely that this entropy production is bigger than the power squared, 2 times the power squared divided by the constancy. Now, if you take all that together and you do some algebra, then you basically end up at a trade-off between power, efficiency, and constancy. And the way to read it is the following. So you would want to have a machine that is very powerful, very efficient, and very precise. But you can't have all of it because the product of P, that thing you would also want to have very big because you would want to have eta close to Carnot efficiency. And you would want to have a small delta P. So you would also want to have that term very big. But the product of the three must be smaller than 1/2. So that is clearly showing that there's a trade-off between these three things. And to illustrate that, we were using a quite established, very minimal model for a solar cell. So a solar cell is just a heat engine that is coupled to the environment and the temperature of the sun. And you can formulate that just as a 2-state quantum dot that is connected to a bath of electrons at a low potential and at a high potential. And just by a photon hitting that quantum dot, you can produce a current that is working against that drop of chemical potential. And we were tweaking the parameters of that engine such that indeed one could get a finite power. So here we are showing as a function of some parameter, the power that is staying finite, while also we are getting close to Carnot efficiencies. That's the ratio between efficiency and Carnot efficiency. And you see that is going to 1. while we have tweaked it such that the power remains finite. But what you can also see here is if you look also at the fluctuations of power, these must diverge in that limit. So it's a yes, but answer. You can get Carnot efficiency at finite power, but you will get a very unstable machine. Now let's move on to something quite different. I've talked about these heat engines, but another different or another interesting topic of this conference is active matter. And I think much more is to come about that, but I will just work with the very simple concept of active matter. That is just a bath of particles that all have their own self-propulsion. So it's a non-equilibrium bath. And many of you might already know that famous result from the Di Leonardo group where they put some asymmetrically shaped cork into a bath of active bacteria. And you can see something that you would never observe in a classical heat bath, namely that this is starting to rotate spontaneously, just extracting motion from a single bath. Now you could imagine that you can turn that very easily into a engine producing mechanical work if you're using that rotation to lift a weight. So that is the concept of a machine that we had in mind, but this two-dimensional setup is still quite complicated. So we've tried to simplify it a bit, and we were looking, instead of that rotational motion against some torque, we were looking at translational motion of something maybe shaped like this chevron-shaped particle against some external force. And of course, it shouldn't hit the boundary. It should always progress through that box. So we need to impose periodic boundary conditions. So you can imagine this is moving along a one-dimensional rail, and we want it to move in a persistent direction. And the model that we are using, let me just very briefly explain that. We are using just Langevin equations once for the motion of that passive particle driven by that external force and in contact with some interaction potential with those active particles and some noise. And for the active particles, we use some active force acting in a direction that is subject to rotational diffusion. And it's also interacting via that potential. And then we can look at the output current, that is just the average speed of that passive particle. You can quantify the extracted power, that is just the external force multiplied by that current. And we can compare that output to the kind of input that is given by the active power. And we just take these active forces driving the active particles and multiply that by the direction in which they move or the speed in which they move. And that is giving us the total power that is injected. We call that the active efficiency, the output power divided by that active power. And now the question is there some kind of ideal design for such an active engine? And we were just at first doing numerical experiments, basically. And we soon found out that we need to focus on slow rotational diffusion, because if the rotational diffusion of the active Brownian particles is very fast, then they just behave like passive particles, and we already know that we cannot extract power from them. So what you see here are some sample trajectories of active Brownian particles that rotate very little. So that's why they look so straight. And you see the idea would be that a particle that is moving to the right, like this 50-degree angle, would get trapped in that chevron, whereas the ones that are going in the wrong direction, so to say, they just bounce off and they do not contribute to the extraction of power. And now we could calculate the output power and efficiency as a function of the external force. And if there is no external force, then obviously you cannot extract any power. And then there is a sweet spot at some intermediate external force. But if the external force gets too strong, then you just see that we cannot maintain that current, and it will just ratchet backwards again. So it always looks a bit like that. And we were thinking maybe the ideal engine would be one that traps all the particles moving to the right and lets pass all the particles going to the left. So it works a bit like a diode. I can't really tell how we would build that. So this is just an idealized theoretical concept. And the nice thing is that for this engine, we can calculate everything analytically because it works so simple, and we can calculate the power and efficiency, and we get this curve here analytically. Then we thought, oh, that must be something like the Carnot efficiency in that business of active engines, and we tried to prove it, but somehow we couldn't. And instead we tried, oh, maybe there's a chance to break that bound. And indeed, after lots of thinking about it, we came up with an even better design. So we found that if we use these kite-shaped particles that have these long tails, but also little wings, then in fact, we can extract a tiny bit more power than what we believed would be that ideal engine. The way it works is basically that it also can extract lots of power from the particles that are going in an upwards direction or downwards direction, like the green one, that is helping to push it even further, while normally it would just go upwards and not contribute much. But you can also see that even this highly optimized machine is not producing much power. So in fact, here it's on the scale of 10 to the minus 3. And at first we thought, well, that's just the way it is. These active particles, they produce lots of waste dissipation, and they're going in the wrong direction. There's just no chance to extract more power than that small amount. But still we were trying to look not just at single active particles interacting with these obstacles, but at a whole bunch of them. And what we were using is basically the same approach, but just as a simple next step, we were looking at many active particles that do not interact with each other. So the red particles don't interact with each other, but they all jointly interact with that blue passive obstacle. And in that setting, we can use a very simple mean field approach. That is, at first, we look again at the motion of just a single active particle, which we already understand. And we just assume that all the input that comes from the other active particles can be just put into a force that they all generate that comes from that interaction force with n-1 other particles. That is just added to the external force. And now we can, because we understand a single particle dynamics, we can calculate the interaction force between that one particle and that obstacle. And in the end, that has to be self-consistent with what we put in there. So we get one unknown, that interaction force, and we get one equation, which we can solve. And that basically gives us, in the end, the output current, which is just the mobility of that passive particle, multiplied by the force, the external force, plus the force that is coming from the interaction with all the active particles. Now there was a big surprise, because once we were calculating again the power and the efficiency of that engine, we were at first seeing basically the same shape, that the filter is what we can calculate analytically, the chevron is doing worst, and the kite is doing like 3% better than that filter. But very surprisingly, now we're no longer on the scale of 10 to the minus 3, but on the scale of 10% efficiency, which is quite considerable. And in fact, this is some collective effect where you can see that particles are helping each other in pushing that obstacle. And that way they can produce a much more efficient extraction of mechanical work. And yeah, so with that, I'd like to conclude. So the first thing I told you about is that thermodynamic uncertainty relation, and I was just discussing it very briefly. If you would like to know more about that, there's a very interesting recent review paper by Horowitz and Gingrich that is a very quick read in Nature Physics. And there you'd also find all the citations to the more in-depth work. And I've also shown you how we have used that thermodynamic uncertainty relation to formulate that trade-off between power efficiency and constancy in heat engines. And more recently, I've actually much more been working on these engines driven by active matter, and we could show that there is some optimal design and also that collective effects can very much boost the power of these engines. So with that, I'd like to thank for your attention, and I'm very much looking forward to your questions.
Thank you very much, Patrick. So we have time for a few questions.
May I ask one?
Of course, go ahead.
You have shown plots for efficiency and power as a function of the force. Can you just tell me what is the normalizing parameter for the force? Yes, Fx over, yes, no.
You mean that solar cell?
Further to the end.
You mean that or the active?
Active one, active one.
Sorry.
Yeah, here. You are plotting as a function of the force. What is FAC?
Sorry, I wasn't explaining that properly. So here we are just looking at a single active particle, and the scale that sets that output. We just wanted to have a dimensionless scale. That is the way we normalize it. We are just looking at power that is produced by a single active particle just in free space. So we have that active force propelling that particle, and then the velocity of that active particle would just be its mobility times that force. So we're just ending up with the mobility times the force squared as a kind of reference of a free active particle. But this is not a true input power here, because it's not a free active particle. It's interacting with that machinery. So that's why we are looking once at the power, and the efficiency. For the efficiency, it's not quite the same input, but it's on a similar scale. So that is why it's a nice way to plot it. No matter whether you look at the efficiency or at that scaled power, it's here always on the scale of 10 to the minus 3. Does that answer your question?
Sorry, I had to mute you, Gatien, because there was a return. Please unmute yourself.
Okay.
Sorry.
Just the question I wanted to proceed and go further in my question. Have you tried to plot the power as a function of efficiency? Because you have these nice plots where, I mean, they are at least for thermal engines, and in the linear regime, you know very well what is the shape, and we have shown also for nonlinear engines that the shape is the same. So have you tried for these active engines to plot this kind of curves?
We haven't looked at that so much yet, but it might actually be interesting. That's a good suggestion. So I think here we are pretty much in linear regime, where I think power and efficiency would just be proportional to each other, more or less. So that would not tell us very much about it. But in fact, once we have these collective effects, maybe it's a bit more clearly visible. These are not all parabola here. This is indeed a more non-linear regime. And yeah, I think that's the next thing I will look at. What does that curve look like? I don't know.
Okay, cool.
Thank you.
Yes. Anyone else? Question? So Patrick, I had just a quick question about this solar cell model that you have. Is that something that can be exploited for real solar cells, or this finite power at Carnot efficiency?
Well, I'm not an engineer. I cannot really answer whether it would save us in the climate crisis. And it's a very idealized concept of a solar cell. But yeah, I mean, these considerations could also be applied to more elaborate models. And even if it's not giving us a new design of solar cells, it might at least be a quantification of how close they can operate to theoretical limits. That might play a similar role as the Carnot efficiency has played for classical heat engines, even though no steam engine actually works close to Carnot efficiency. It's setting kind of the stage for what can be thought about.
Okay, yes, that's very interesting. Thank you.